So thank you everyone for standing by. We can start, I think. Welcome to today's webinar from Bjørn Thorsen and Lubrizol. It's a joint effort and we're happy to have you here. So today's webinar is on a new generation of sustainable TPU solutions. It will be brought to you by Miguel Navarro from Lubrizol and Mikko Langstrom from Bjørn Thorsen. I remind you that the session is being recorded. The audio is muted, but we will have a Q&A session right at the end. The presentation will last around 30 minutes, so that should give you plenty of time to ask questions and engage with us. In the meantime, you can use also the chat dialog box to make any comments. And for the Q&A dialog box, it's very easy to find. It's just on the right-hand corner on the bottom of your screen. After today's webinar, you will be getting a copy of the recording. And without further ado, I think we can let Mikko take over.
Okay, thank you, Lydia, for the warm welcome. And let me say that it is our great pleasure also from the Bjørn Thorsen side to be able to join forces with Lubrizol and do this webinar and show this to customers and companies in our territories where sustainability certainly has been a very hot topic for many years now. For those who don't know who I am, my name is, as Lydia mentioned, Mikko Langström, and I'm the sales director for plastics at Bjørn Thorsen. First of all, I'm so happy to see so many of you joining us today, and I hope that you will certainly find these topics very interesting and will be able to also take some good learnings with you from the webinar. For those of you who don't know Bjørn Thorsen so well, and what are we doing here together with Lubrizol, I have two slides to show you before I hand over to Mikael for the main part of the presentation. So Bjørn Thorsen is a distribution company established in 1952, and as its main business is chemical distribution. BT, as we call ourselves, was appointed as the Nordics distributor for the predecessor of Lubrizol Engineered Polymers, BF Goodrich, already in the 1960s. So we've been actually collaborating quite a few years already. As the business today, our distribution activities have started in Denmark, and the expansion of the activities has been done mostly in the last few decades, starting in the Nordic and Baltic countries, and most recently in the early 2000s in UK and Ireland. Here you can see a map shortly about of our locations. You can see we have warehouses in 3 Nordic countries as well as in UK and Ireland to ensure fast deliveries to our distribution customers. Please, Mikael, jump to the next slide. Yeah. So what is Bjørn Thorsen doing apart from the distribution? We are today, of course, a distribution partner, as mentioned. We sell Lubrizol at Engineered Polymers through our Advanced Polymer Solutions business unit, and Lubrizol is a strategic partner for us. We also work not only on the engineered polymer side, but we also work on the life science health portfolio. So we are distributing today not only the estanes and pearlthanes, but also the pellethanes and isoplasts from Lubrizol in our region. Additionally, in addition to the distribution business, and more recently, we've also started to work together on development projects where we are aiming towards, maybe you could call them common strategic goals. And from our Bjørn Thorsen side, a lot of this work is done at our affiliated company, Customized Compound Solutions, or as we call them, CCS, that are focusing on producing specialty TPEs, such as TPU grades that could be bonding grades or customized color TPUs. And more recently, we've also worked very heavily with the Lubrizol R&D team to address new demands from the, you could call it the liquid coating industry, to find solvent-based TPU systems that would be less harmful than the conventional solvent-based TPUs. And I will come back to this later after Mikael's part of the presentation. So that was a short introduction about us, but now without further ado, let me lead you to the main topic of today, which is again a new generation of sustainable TPU solutions, and that will be presented to you by my colleague from Lubrizol, Mr. Mikel Navarro. So please go ahead, Mikel.
Thanks a lot, Miko. So as it was previously said, we are giving you a snapshot of our next generation of materials bringing sustainable solutions from Lubrizol. About me, I'm an application development engineer at Lubrizol. I have been in the company for about nearly 5 years, and I have a previous experience in the plastic business, process, product, application development, both at commodity business and materials and high-end polymers and engineering. Let me talk to you briefly about Lubrizol for the ones that are not so familiar. So Lubrizol is a company part of the Berkshire Hathaway portfolio, which is owned by Warren Buffett and includes over 60 companies all around the world. Lubrizol was established in 1928. We are a chemical company, fairly diversified. We have our headquarters in the US, in Ohio. We are at this moment over 8,000 employees, and we have a footprint in more than 100 countries in all the continents, providing support to customers worldwide. Sustainability at Lubrizol has always been important. We defined our mission as move cleaner, create smarter, and live better. We can say that more than half of the world population has been exposed at some moment to some of our Lubrizol products or interacted with them, both from our additive solution business or from our advanced materials division. For us, sustainability is not new. It's something that we have been doing in the past, over the last years, because at the end it impacts many areas of the business that we develop. So we have processes. We are trying always to reduce energy consumption. We introduced biomaterials long time ago before the sustainability boom. And always for us it's important to reduce the waste and the emissions that we generate. These are previous incentives, and at this moment sustainability also has become a very hot topic. So it's something that we are proud to say that we have been looking at for quite some time already. So we have decided out of the United Nations Sustainable Development Goals, as you know, there are 17, and we can see that we can make impact in 7 of them. So you can learn more about this in our corporate sustainability report that you can find in our website. So as I mentioned before, our goal is to make an impact and provide benefits from a sustainability point of view when we are trying to develop these new products, as I said, with the mission of move cleaner, create smarter, live better, but also from a corporate citizen standpoint. So we care about the environment, the social impact, and the relationship with governance when we do our business. About the division that we are talking today, Lubrizol has 2 main divisions. One of them is advanced material, and within that there is stain. That is the one that is represented also by Bjørn Thorsen. On this one, we are proud to say that we invented TPU in 1959. We are the heritage of BF Goodrich, as Miko previously mentioned, and we were acquired by Lubrizol in 2004. And we have been part of the Berkshire Hathaway portfolio since 2011. Our brand is Stain, is well known due to the different aspects and materials that we can cover. We have a very wide portfolio, and our materials basically are covering the gap that there is between the rubbers and the rigid polymers, bringing some unique properties where other materials cannot perform. We like to collaborate with our customers, and as we previously mentioned, we have a global footprint in all the continents with different manufacturing sites to ensure availability and supply. TPU is a material that is very versatile, so it has quite some unique properties which allow them to perform in conditions that other materials cannot. You can see in this slide some of the properties that we can show pride about and the uniqueness of TPU. Being a thermoplastics, one of the most important one is that it can be thermoform and conform through a standard processing in industry like injection molding and extrusion, which also means that over time it can be also recycled back to the original materials and reused again. We have quite some specialty grades that cover again different aspects of the needs in the industry, and we continue to grow it through innovation. Why Lubrizol? Why it's work with us? I mean, as I mentioned before, we have a wide portfolio. We have a great distribution network, including Bjørn Thorsen, as you know, which is very efficient. And we are application savvy. We know from the starting of the formulation of a polymer, the processing, the application, and the use of the materials. We bring over there knowledge both from our R&D, manufacturing, sales, to make the experience of using the materials one of the greatest in the industry. Let's go directly to the main topic about sustainability. So, as you know, at this moment, materials are used in different ways. So society uses them. They are produced coming from a very complex, let's say, value chain. And then after the use, unfortunately, at this moment, most of the materials end in the landfill or incinerated. This is something that we want it to change, and the industry will change over time. So ideally, over time, we will run out of this landfill disposal, and materials will become into this what is described in this slide, these different cycles. Once the material has been used, you can do different things. You can just reuse, which is one of the best alternatives. So use again or find secondary uses to the items that have been made. You can also recycle in a polymer cycle. That means basically you take the items and again, you scrap them and you reuse the grinds to make again new materials. This would be, for example, a way of mechanical recycling. There is also what is known as the monomer cycle, which would be more known as chemical recycling. Basically, you take a material and you break it into the repeating units, so you can recover these monomers and use them again to make plastics. There is the energy cycle. Basically, out of incineration, you can obtain energy, and you can obtain also you are emitting also CO2, which will incorporate to the atmosphere, and again, it can be recovered in different ways. One of them is obviously biologically, the plants will capture the CO2 through photosynthesis, and then they will produce some biostocks. So from our point of view, we have looked at all these different options, and we have decided to focus in 3 of them. One of them is what is known as our bio-TPU, which is a material which, again, takes this biological CO2 cycle. It's incorporated into plants, and these are used as feedstock into making some components that are used to make TPU. Another approach we have also incorporated is what we call stain R&W, which again, from these biological CO2 cycles, some plants through photosynthesis incorporate the CO2, transform it into carbon, and we introduce it early on in the processes of the petrochemical industry. And last, we have also what we call a stain PIR, which takes materials in the polymer cycle, and after end use or after the production, some of the scraps that are produced, we recover them and we use them again to make new polymers that are fed into the industry to make new articles again. You may ask about the monomer cycle. Due to the complexity of TPU, we don't deem it as the most convenient option to recover, as TPU is a fairly complex chemical molecule, and it's technically very complex and sometimes even not environmentally coherent to go through this monomer cycle due to the complexity on the chemistry. Let's talk briefly about TPU, the structure and the chemistry. Some of you may know, just in case I'll explain a bit further. TPU is formed by 3 components that we call, one of them is the isocyanate, second one is a short diol, and finally is this polymeric diol or polyol. The isocyanate and the short diol create what we call the hard segment, which are, let's say, more rigid polar portions of the molecule, and then the soft segment is made by the polyol, which brings the flexibility and again is a more apolar region that again can conform and stretch. This basically what it produces is that when you have the polymer chains in a molten state, they can freely move. So this allows basically that you can extrude, injection mold the material as it's, let's say, in a liquid state, and it can take different shapes. Later on, when the material cools down, after you, for example, inject an article, the hard segments find each other and create what we call over here these crystalline domains that are physical anchors that would act as crosslinks in thermosets, although that is, in this case, they are physical bonds, which again can be reverted with temperature. So that's the beauty of the material, that it can be thermoconform and processed with traditional plastic processing methods. This also produces that these anchor points create, let's say, links between different chains, which at the end allow that when the material is stretched, as you can see, for example, in a typical tensile test, this brings elasticity, but again, as this cannot displace as the physical anchor points are fixed, the shape will return after you remove this strain. So this brings the flexibility to the material. So this is briefly how TPUs are made and why the properties, the elastic properties come without the need of have covalent bonds as in thermosets. At this moment, TPU is done basically the main way to obtain TPU in industry is you start from fossil origin, oil or gas. These are fed into refineries, which produce a variety of basic chemicals, methanol, acetone, phenol. These materials are fed into other chemical facilities, which use different of them to produce the three components that I mentioned: isocyanates, diols, polyols, which are the raw materials used by TPU producers to obtain finally at the end by the reactions the molecules, the polymer of TPU. However, I mean, there is not just one TPU. We are not just talking of a basic, simple, unique molecule as we would be talking about polyethylene or polycarbonate. You can obtain with the same three components of isocyanate, diol, and polyol a variety of TPUs depending on the ratios, and this will bring you a variety of hardness and fluidity of the materials. Not only that, when you start looking also that you don't have just one type of isocyanate, but you can play with the isocyanate chemistry, you can have different diols, and certainly we have different polyols that bring the unique properties to the TPU. You have quite a variety of portfolio of different TPU grades. We are talking about hundreds. This brings us to think there is not no plant or bacteria or live being at this moment that can produce such a uniqueness and variety of products. Which makes think that you cannot obtain this directly from nature, but you have to be looking back at the original components to incorporate them from a biogenic origin to bring some sustainability aspect into making TPU. This is where we have come, and so we have three different routes, as I mentioned before. We have bio TPU by Lubrizol. In this case, what we do is that we use from a biological process, we obtain one of the components that is needed to make this polyol. And this polyol will contain a repeating unit that is fully and completely from biological origin, and this will go into making the repeating unit of the TPU. With an example over here, we would have, for example, this type of molecule over here, which contains green carbon. And these repeating units as a whole, they go into the production of the polyol, which later on is incorporated. So you will have complete green, traceable by carbon-14 carbon units that get incorporated into the polymer, as I mentioned before, as a part of the polyol. Another approach that we have also taken is stain R&W. In this case, what we do is basically we introduce the biogenic carbon containing raw materials earlier in the process. as I mentioned before, at the end, it's complex to have the exact diols and polyols obtained directly from plants. So another approach industry is taking is to introduce, let's say, simpler materials. So in this case, from crops, biomass, there is a fermentation, and we would be obtaining biomethane. This biomethane is fed into refineries, crackers, as in combination or mixed with other oil-based raw materials. So at the end, we are reducing part of the consumption of the fossil oil-based raw materials at the end to obtain the same basic chemicals. But you will understand also that on this each of these materials there will be a mix. Part of it will be coming from biogenic origin, so the products will contain a mix of green and oil-based carbon. This has been optimized for different chemicals available in industry, and it will be used. We will purchase these sources to incorporate them into producing some of our materials. So, for example, for polyols, this means that in the polyol or in the TPU, you will contain a mix of. You will find a mix of carbon-based, oil-based, and bio-based carbons. And this, how it's handled in the industry, basically, there is a process, an audit and traceable process, which basically allocates the amount that has been fed originally as biocarbon to a specific product, just to make sure that no more than that is allocated, and you can just trace and, let's say, allocate it to the end user that is valuing this incorporation, which at the end reduces the overall consumption of oil or gas-based, fossil-based components. This is done with different external companies, can be traced, and at the end leads to materials that basically are identical as if we had done it directly from fossil raw materials. Because as I mentioned, at the end, what you are incorporating is either biomethane in this case or standard methane from oil industry. So the end product is exactly the same, indistinguishable from a traditional oil-based TPU. And the advantage of this process and this way of incorporating the bio-based raw materials is that this can be extended, and industry is working towards that, into different components, for example, like isocyanates, which are very complex to obtain, let's say, from a natural route. So overall, over time, we will be developing more materials with this biomass balance strategy. To further explain, I mentioned, this is verified by independent companies that basically trace and allocate the amount that can be produced or can be sold containing this biogenic carbon. It leads to exactly identical final products, indistinguishable, reduces the consumption of these fossil derived raw materials, and again, we are using the existing assets and bringing all the efficiency they have developed over time to work in optimum process conditions. To put it as an example, this would be, for example, like the case of the electrical grid. The electrical grid, at the end, you have connected different producers of electricity, like nuclear, combined cycles from gas, carbon, but you also have greener options, like hydroelectric, wind, solar. So at any moment when you switch on the light, you are getting a mix of all that. And then it's up to you to decide if you buy from a distributor that, again, gives more priority to green electricity, which, again, will create more demand for this and will favor the construction of more of these assets and utilities that, again, they are bringing less consumption of fossil fuels. So these are graphs basically from industry. You can see that at any time of the day, at some moment, you will have larger production of solar energy, which at the end will be incorporated into the electricity grid. So the electricity you get is a mix, but at the end, by going and buying electricity from distributors that incorporate more or demand more green energy, it will allow a reduction of the consumption of fossil-derived energy. Finally, we have what we call STEAM PIR. In this stands from post-industrial recycle. And in this case, what we have done is we have worked closely with some of our large customers that, again, whenever there is a transformation process, there are always some scrap or waste generated. You are starting the machines, extruders, you are having some, you may be having some quality or cleaning at the beginning. So there is some scrap, or you may not use 100%, and there may be some trims generated in the process. So there is always some scrap or loss in the production of items. So we have worked closely with some of our customers to take back, return these scraps. We know them very well because they are our materials. So what we do with them is we reincorporate them, we take them to our facilities, we fully analyze to make sure that they are in prime condition, they have only been processed once. We correct them if needed by adding some virgin material just to make the best of them and match the properties. And this later on gets sold with standard TDS and certificate of analysis as what we call STEM PRR products. Now I'll give you some numbers or some idea of how the different approaches affect in terms of global warming. So this would be just in percentage what would be a standard polyether TPU, a fairly common product, about hardness about 98. When we look at the equivalent product made with the stain R&W with the bio-based approach, we are looking at a reduction of about 20 to 25% of the CO2 emissions to make this same material. These are emissions that we measure on what is called by the LCA methods as cradle to gate, which are the emissions that include the raw materials inputted to make that we buy to make the products, the energy we use to make our process, and the emissions that we release to the atmospheres in our facilities. So by incorporating these bio-based derived components from the with biomass balance concept, we are reducing the CO2 emissions for the same amount of TPU by 20 to 25% on this specific rate. In the case of bio TPU, equivalent material with hardness 98, again, we are seeing a reduction of about 30%, 30 to 40% compared to a similar TPU of equivalent properties. And finally, the one with the largest reduction would be STEM PIR. In this case, as we are not using raw materials because we are using TPU waste generated by our customers that otherwise would be going to landfill or incineration, basically there is no scope 3 emissions. There are no scope emissions related or CO2 generation related to raw materials because they were already going to be disposed. So using the established cutoff rules in the calculation of the LCA, we are just including over here the contribution for the process of recovering the materials and reprocessing them back into new materials that have the proper quality to be sold. And this accounts about a reduction of 80 to 90% to a comparable TPU, as I mentioned before. I'll give you some examples of our materials. So for the bio TPU, this some of you may know, we launched it about 10 years ago, and it was the first bio TPU available in the market. Before this recent sustainability boom, this was had a place in the market, but it was mainly value because the unique properties it brings. As I mentioned before, it generates a new polyol which has some unique properties, and in this case makes TPU with great hydrolytical stability, which is nearly matching the one of polyether TPUs. And it also has a very good clarity. So the transparency is also value for some of the applications that it brings clarity and allows differentiates from other materials that have a higher yellow index. Using this chemistry property of TPU, of Lubrizol, we have developed a portfolio of different materials with different hardnesses, as you can see in this table, ranging from 82A to 52D, with a variable amount of biogenic carbon. In this case, as I mentioned before, as this renewable component is incorporated in different ratios, basically to lead to different hardness products and different properties, let's say, for the applications that we target. Stain R&W, we have at this moment one grade, is a mass balance bio-based. And in this case, we are using 50% of biomass balance stock. to make it. And as I mentioned before, this has identical properties and is a drop-in solution as a replacement of our current polyether grade stain 58887. That is a grade that has multiple play applications, mainly in the extrusion market, as you can see over here, in making belts, tubing, hoses, and so. With this approach, at this moment, as I mentioned, we only have one grade, but we plan to develop a further portfolio and incorporate more grades in the future. So feel free to talk to us if you have a specific demand, and we will look into it to see if we can also translate it with this biomass balance approach. And last, on the PIR approach, we have also one grade at this moment. This is a grade that we obtain from one major application, so we have a stable supply to ensure the surety of this one. And we have, as I mentioned before, when we receive it, we make sure of the quality of the incoming scrap material that has been processed, and we correct it if needed, just to produce a material that has consistent properties, as I mentioned before, reflected on a TDS and guaranteed by a certificate of analysis meeting these TDS properties. As I mentioned before, this is the lowest CO2 involved on this one. And again, we are also open to talk to different customers if they have scraps that, again, could be interesting to incorporate to make new PIR products, or are interested in using materials, as I mentioned before, with the lowest CO2 emissions, as would be this case. Again, we have this material also available for sales and sampling. With this, I conclude my presentations. I would just like to remind in that case that we have taken three approaches: the bio TPU, which creates unique polymers with unique properties by incorporating biogenic repeating units. We have the stain R&W that produces exactly identical as oil-based polymers by incorporating renewable components early on at our suppliers as raw materials for them. And the stain PIR, which takes post-industrial recycle and makes material with very good properties with the lowest CO2 contribution for the environment. You can learn more about this in our, we have a sustainability video that we will paste later on in the chat, so you can go and watch yourselves later on. Thank you very much. And with this, I would like to conclude and pass again the word to my colleague, Mikko at Bjørn Thorsen.
Sorry, my microphone was off or above my head. So yeah, thanks, Mikael, for giving this overview of your sustainable TPU solutions that Lubrizol offers to the market. As mentioned previously, we also collaborate. Bjørn Thorsen also collaborates with Lubrizol on bringing some additional products to the market, and here I will give you a very short overview of these. So here you see a page of basically CCS developed products together with the Lubrizol R&D team that are solvent-based TPU solutions, also geared for the future sustainable demand of the market. These are basically results of roughly 3-4 years of development, which is still ongoing, and where we are looking into solution-based TPUs that would be equally as effective to dissolve Lubrizol TPUs as the conventional solvents, but that would also have an improved regulatory profile compared to the conventional solvents that many customers are asking for these days. Through these Optisol polymer solutions that are targeted for processes that can handle liquid systems, CCS can offer to the market today less volatile, less harmful, and even bio-based, solvent-based TPU formulations. So here you can see on the bottom of this slide just a quick comparison between what kind of TPU solutions are used mostly in the market today and what kind of hazard labeling and hazard statements do these normally incorporate. And on the right-hand side, you see the kind of solutions that we at CCS are working on and are offering to the market. Very good. And Mikael, if we jump to the last slide, maybe to summarize and wrap up today, I can see we've been using very efficiently our time. We've been talking about sustainable TPU solutions. I hope everyone has enjoyed the presentation, and I can see that there's come some interesting questions from you guys as well. I hope that with these products and solutions we've presented to you today, you are also convinced that Lubrizol, as well as BT as Lubrizol's distribution and development partner, are looking to bring you solutions that will address the sustainability challenges that you might have in the future. And with our collaboration together with Bjørn Thorsen and Lubrizol, and the wide range of products Lubrizol has, and the agile and quick customization opportunities that we can offer at CCS, we believe that in collaboration with you and your demand and your needs, we can bring certainly added value to your products and essentially high value products to your end customers. With that in mind, I actually hope that we have already started collaboration, and I can see that you've sent a lot of questions to us. So we will try to answer some of these questions, and therefore I would like to hand over the microphone back to my colleague Lydia, and who will be facilitating the Q&A session.
Thank you, Mikko, and thank you, Miguel, also for the presentation. We do indeed have quite a lot of questions. Let's start. The first one being regarding the TPU, is this also recyclable at the end of life?
Yes, I'll take that one. Yeah, for sure. I mean, the TPUs are inherently recyclable materials. TPU stands for thermoplastic polyurethane. So the materials, again, I mean, they can be grinded back and molten to obtain pellets or to take another shape. That is one of the key properties of thermoplastics as opposed to thermosets, which are mainly the other rubbers and silicones, which contain chemical crosslinks. So those ones you cannot recycle. You have to basically break them thermally, while in the thermoplastic, the bonds that create the elasticity, they are, let's say, physical bonds that are released with temperature. So you heat them, shape them again, cool them, and you would have a new material that makes them totally recyclable.
And maybe I can add to that if someone is wondering whether you can also recycle the bio-based TPUs, Mikael, I guess we can agree that yes, the bio-based TPU, as it is not the bio is not a filler or an additive into the TPU, you can recycle this in a conventional TPU stream without any issues. Correct me, Mikael, if I'm wrong, but that's just an add-on.
That's again, I mean, also TPUs have good mixability. So yeah, bio-based TPU, it's thermoformable and recyclable as any other TPU.
Thank you for that question, and thank you both for the responses. The next one refers to an earlier stages of the presentation. It says, how can I avoid isocyanate degradation in a high temperature? And what is the maximum extrusion temperature in Celsius?
Yeah, that one normally in our processing guides, we give you the recommended conditions. So as long as you process within the given guidelines, there won't be isocyanate degradation. Materials start to degrade when you go above 260 degrees and so. So processing them at the given conditions won't release any isocyanate.
Okay, thank you for that question. The next one is, what kind of crops and biomass is being used?
Well, on the ones for making the bio TPU, that's Lubrizol proprietary information. What I can say is that we use non-food based derived biomass. So it doesn't compete, and it doesn't create any burden on the, let's say, food industry feeding needs and so. In the case for R&W, the raw bio-based are incorporated by our suppliers So again, they can be diverse. They can go from pyrolysis-derived oils obtained from pyrolysis of plastic waste, also to vegetable or forest-derived residues. For example, from different farming operations, the scraps from food production and so on.
Okay, thank you for that question. Thank you for the response. There are two that are similar. The first one being, is the bio-based source from second generation? And there's another one that asks, are the biomasses you use first generation or leftovers from other processes?
Yes, as I mentioned, I mean, the bio-based, I don't know the detail exactly or on the generation itself. Let's say for making the bio TPU, it comes directly from a harvested specific feedstock, while for R&W, it contains a mix, as I mentioned. It can contain from residues from food industry, forestry, and so, or derived from pyrolysis of waste or different technical options that can be used to generate feeds for the crackers and the chemical industry.
Okay, thanks for that question. There's one more that's asked, which LCA software did you use?
Yeah, for LCA at this moment, we are using CIMAPRO. And we use existing primary data that we generate from our facilities. We have calculated after complete evaluation of our emissions and consumptions, as well as secondary data from industry and primary data obtained from our raw material suppliers when available. For the main raw materials that we use to make TPU, we have it available directly calculated from them.
Okay, I think that we have time for just one more, and it's for the different sustainable TPUs, what are the actual percentages of bio-based or PIR content for the materials?
On this one, basically, for the bio-base, as I mentioned before, it's a variable depending on the product hardness and melt flow. So again, it ranges between, I think it's 32% and 67% bio-base according to ASTM norm. For the R&W, we are incorporating it at this moment in one of as a form of one of the components. So it's about 50% of the carbon comes from biogenic origin. And we are looking and working with our raw materials to incorporate further as into more of the components that are needed to make the TPU. In the case of PIR, we are, in theory, we are incorporating 100%, but as I mentioned before, we add some fresh material to slightly correct it. As you know, the material has been processed. So it, in some cases, and that's also when we bring the value, we correct it to make sure that the processing is equivalent to virgin materials. So it contains a variable amount up to 10-20% of fresh TPU just to correct, in this case, the mechanical properties and the processing properties of a material that has been already been exposed to a thermal cycle.
Okay, thank you very much, Miko and Miguel, and thank you everyone for joining today and for all your questions. We're coming to the end of the webinar. I'd also like to thank Catalina Slipka for the organization and the work behind it. We hope that you have found it interesting. You will receive a copy of the webinar recording. And before you leave, feel free to click on the links you will see on the screen. We are going to share our sustainability video with you. Some of the windows that pop up just mean that you need to accept those. You can also have the link in the chat, so you feel to also go there. And we look forward to seeing you in any future webinar editions. It was great to work together with Bjørn Thorsen. So thank you, Miko, for the opportunity.
Thank
Would you
you
like to
everyone
say
for
any
attending.
final words?
Yeah, I can say, well, thank you everyone for attending today. And yeah, like Lydia said, hopefully you find it very interesting, and we look forward to hearing from you. If you have any additional questions to these already answered during the in the end of this webinar.
Yes, please do contact us. Do contact Mikko if there's anything still left to be answered or to comment. We look forward to hearing from you. So take care, everyone. Thank you.
Thank you.